Let's take a fun journey to the amazing world of the brain's plasticity, its ability to adapt, learn, and remember. Imagine your brain as a super flexible, ever-changing universe of connections. One of the key players in this process is synaptic plasticity, which is just a fancy way of saying that synapses, the tiny junctions between neurons, can strengthen or weaken over time. This flexibility is fundamental to learning and memory. A superstar in this arena is hippocampal long-term potentiation. Think of LTP as a kind of neural high five. When two neurons frequently communicate, the connection between them gets stronger, making future signals easier to pass along. It's like practicing a dance move until it becomes second nature. This process involves receptors like AMPA receptors, which respond to the neurotransmitter glutamate and play a vital role in strengthening synaptic responses during LTP. How do neurons know when to get stronger? Enter brain-derived neurotropic factor. BDNF is like the brain's own growth fertilizer, promoting synaptic growth and plasticity. It can influence dendritic spine remodeling, which is the reshaping of tiny protrusions on neurons where synapses form. These spines are dynamic. They can grow, shrink, or reconfigure, allowing the brain to adapt its circuitry based on experience. Speaking of restructuring, the extracellular matrix, the supportive scaffold outside neurons, also plays a crucial role. It contains molecules like tennyson R, reelin, and chondroitin sulfate proteoglycans, which can either facilitate or hinder plasticity. For example, reelin helps guide neuronal positioning and synaptic stability, while chondroitin sulfate proteoglycans cannot act as a sort of brake on plasticity, making the environment less permissive for change. Within neurons, various signaling pathways regulate these processes. For instance, eukaryotic elongation factor 2 is involved in protein synthesis, which is essential for maintaining long-term changes at synapses. The mechanistic target of rapamycin, or mTOR, is another key regulator. It controls cell growth and protein production, underpinning the structural and functional changes during plasticity. Metabolites, small molecules involved in metabolism, also influence plasticity. For example, certain metabolites can modulate signaling pathways that impact synaptic strength. Speaking of signaling, the paraventricular nucleus of the hypothalamus contains corticotropin, releasing hormone neurons, which are involved in stress response. Interestingly, stress can impact synaptic plasticity, affecting learning and memory. Finally, it's fascinating how all these elements come together in a beautiful orchestrated dance. Synaptic plasticity allows the brain to adapt by remodeling dendritic spine, modifying receptor compositions like increasing or decreasing AMPA reception, and reorganizing the extracellular matrix to either permit or restrict change. So next time you learn something new or remember a cherished moment, remember your brain's incredible ability to rewire itself. Thank you for joining me on the structure working together in the background.